Okay, continuing from the previous video, we now see the connection between Z5, the finite field with 5 elements, lines in these finite geometries, and Latin squares. So just to finish this off, imagine, take the following situation that we were already working on and just complete the picture. What do we have again? We have, not to repeat too much, but we have this finite field, Z5, consisting of elements 0, 1, 2, 3, and 4. We have addition and multiplication on this set, and thus we have a field. With this field, you can generate with simple linear algebraic equations lines. And those lines are just the sets of points satisfying these simple equations. Okay, well, consider the equivalence class of parallel lines x equals k. All right, you have the line x equals 0. This is just the line with x coordinates 0. Oops, that's the line y equals 0. Let's pretend that didn't happen. You have the line x equals 0. That's this line. You have the line x equals 1. You have the line x equals 2, the line x equals 3, and the line x equals 4. Okay, and these 5 lines are all, again, each consist of 5 points, and there are 5 of them, and this constitutes an equivalence class of parallel lines. That is a set of lines within which all of the lines are equivalent, where equivalent in this case means parallel. So it's just a bunch of parallel lines, and these parallel lines pass through all 5 points of the model. Okay, and notice that these lines satisfy simple geometric requirements, such as through every 2 points there's a line. Well, actually not yet. So that's one equivalence class. What's another equivalence class? The equivalence class of the form y equals k. So what does this look like? These are just all the horizontal lines. So here we have the line y equals 0, the line y equals 1, the line y equals 2, the line y equals 3, and the line y equals 4. Okay, no more commentary on this here because I think that's pretty self-explanatory. Great, now you have a set of, once again, 5 points per line. Okay, now you have a set of lines, all of which are the form y equals x plus k. Okay, so this line will be the line y equals x. Then you will have another parallel line. This is the line y equals x plus 1, in which it kind of wraps over here like this. Then you have the line y equals x plus 2, in which it wraps like that. The line y equals x plus 3, and it's going to wrap like this. And finally, the line y equals x plus 4. Okay, and the idea is, again, this is an equivalence class of parallel lines. All of these lines are parallel to each other. 5 lines passing through each of the 25 points. Okay, what about all the lines of the form y equals 2x plus k? Maybe the rest of these I will just do with no further commentary. This is the line. Okay, here it now becomes maybe awkward to, yeah, okay, whatever. I'll just draw it in. The pictures become increasingly hard to understand unless you put a lot of effort in, which I maybe don't want to. But anyway, this goes down now. This is slope 2, also known as slope -3. So we're here, and then it's like that. I think I've done that correctly. Sure I have. And so that's one line. Then you have the line, the orange line. And then that continues down here, and then slope 2, and the line with with y-intercept 2 and slope 2, which picks up over here. It's harder than I thought. Yeah. And then this line with, okay, up. Oh man. I actually think I have screwed this up, potentially. I've totally screwed this up, because this, okay, this is actually harder and taking longer than I wanted it to. We go here. There we go. And yeah, then the green one, is the green one also wrong? No, this one is right. Good job, me. Now we have the red one, which picks up over here, and then here. Yep. And finally, the purple one, which goes like this, and then here. Yep. Slope 2, and like that. Okay. Great. This is okay. What does this have to do with Latin squares? Well, each one of these equivalence classes of parallel lines can immediately be turned into a square. How? Man, you just do it. Here we have an obvious square. I will just put 1 down here because why not? So this is the line of 1s. In other words, that line, that blue line, you just fill in all the 1s. And then you have the line of 2s. It's actually just easier to do it like this. And directly, the line of 3s looks like this. And these lines all have slope 1. In other words, you create the Latin square in such a way that the numbers are all form a line. The lines come from the geometry. And finally, you have the, oh my God, zoning out. This should be 4, of course. Sorry about that. The red is 4. I'll try to consistently do that. And the purple is 5. Okay, 3 more to go. Maybe for these others, I will just go directly to the Latin square. In some ways, I'm wasting time drawing these annoying lines once I understand what's going on. What is this? Oh, so notice that this is a good Latin square because all of these lines are parallel to each other, and so no 2 lines ever bump into each other, and you never end up accidentally putting 2 numbers in the same spot in the box. Okay, how about now? The set of lines y equals 2x plus k. Well, like I said, it's easier to just do it in this grid, I think. Easier on my brain, I guess. So here I'll put the 1s, and now I'll just do all the lines with slope 2. So slope 2, but slope 2 is also slope -3, because 2 and -3 are the same mod 5. So that was, in fact, much easier. Now we'll go to the orange one. The 2 always goes right above the 1. So that is the line of 2s. And then we have the line of 3s, again with slope 2. Then we have the line of 4s. Oh yeah. And then finally the line of 5s. So, wait a second. Something went wrong again. No, it didn't. No, something definitely went wrong. 5. I think I just left out a 4. Yep. That was the only thing that was wrong. Yep, good now. Okay, and then 5, 5, 5. Okay, so now pausing for a moment to appreciate a little bit what's happening here. Because I created these Latin squares geometrically, I now have the property that I wanted out of them, which is that these 2 Latin squares are orthogonal. What does it mean for a pair of Latin squares to be orthogonal? It means that the 2 Latin squares, if you superimpose them onto each other and create sort of ordered pairs out of the entries in the 2 Latin squares, never repeat. And that is obviously true that, for example, in this spot, we have, reading from left to right, the ordered pair 3, 2 occurring in this position. But of course, the ordered pair 3, 2 never appears again anywhere else in the square, because the only way that would happen is if the line of 3's in this geometric model intersected the line of 2's in this geometric model a second time. But that can't happen because two lines can never intersect each other at 2 points. And so this is one of the axioms of this finite affine geometry, one of the basic most natural axioms, that through 2 points that there is exactly one line. If you give me 2 points, there's exactly one line that goes through those 2 points, or equivalently, you can't so that's the existence part of it. The uniqueness part of it says that you can't have 2 different lines that pass through 2 different points. And the fact that this is a geometry ensures that these Latin squares have that orthogonal property. Okay, this time, instead of drawing annoying lines and messing up, I'll just go straight to the Latin square. I will now use my understanding of the finite geometry of lines with slope 3 to just create the Latin square. And what are we going to do? Well, we're just going to write lines with slope 3. So up 3 and over 1. 3 is also negative 2, so I can also go down 2, up 3, down 2. So that's one line with slope 3. What's another line with slope 3? Well, it's that one. And yeah. Then there is another line with slope 3. It's that one. Another line with slope 3 is that one. No. Oh boy. Okay, hold on. Made another mistake by trying to go too fast. Slope 3, slope negative 2, slope 3. So what happened? Slope negative 2, this 3 is an error. So this 3 should in fact go here. Oh no, so that was fine. Maybe that's exactly what I had. And then the slope 4, the 4 always goes right over the 3. Slope negative 2, slope 3. Oh yeah, everything was fine. I just zoned out. And slope negative 2. And the final line with slope negative 2 is this one. And it also could be called slope 3. Okay, and once again, all of the lines in this equivalence class of parallel lines, within this equivalence class, I don't feel like drawing, all the lines are parallel. And this gives rise to another Latin square. And these 3 Latin squares are mutually orthogonal, which is to say that if you take any pair of these 3 Latin squares, they are orthogonal with respect to each other. Of course, because if you have all the lines with slope 1, all the lines with slope 2, all the lines with slope 3, you never get to 2 lines bumping into each other twice. Okay, the final one is all the lines with slope 4, but all the lines, this one's the easiest one because, or it's easy because all the lines with slope 4, that's like all the lines having slope negative 1. And so this time I'll just draw my lines with slope negative 1. For consistency, I'll do it like that. Slope negative 1. Like that. Slope negative 1. Slope negative 1. And slope negative 1. Yeah. Load 2. Okay, so the final thing is, what is there to say about these other 2 equivalence classes of parallel lines? Well, here I also get some lines. They're just, or I also get some squares, that is, but they're not sort of the squares you were expecting. They're not actually Latin squares. They are squares though. So let's just do these. Let's just complete the squares that we have here. So we got and yeah. Very time consuming drawing all these beautiful pictures. And finally, the 5s. Okay, so if I were to bother drawing out these final set, now I'm feeling guilted into actually doing it, but I kind of don't want to. Should I just do it anyway? I guess I can just do it anyway. I have like this line. No, I don't want to. Okay, what do all of these lines have in common? Well, I have 5 lines here, 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 and 5 lines here. And what these, so I end up with 6 total sets. What are these sets? They're the equivalence classes of parallel lines. In this 25-point model, all the lines can either be pointing straight up with slope sort of infinity, with slope 0, with slope 1, slope 2, slope 3, or slope 4. And those are the only possibilities. And so you have, in fact, 6 different sort of directions that a line can point in. This gives rise to 6 different equivalence classes of parallel lines. And within each equivalence class, there are 5 lines with exactly 5 points on each line. And so, as we talked about one day before spring break, you have 6 equivalence classes of parallel lines. You have 5 lines per equivalence class, and so you have 30 total lines. 30 total lines. Okay, and now you see the full complete geometry going on here. The full complete geometry is that in this finite geometric model with 25 points, the following axioms are satisfied. There are at least 2 points per line. In fact, in this particular model, there are exactly 5 points per line. You can even prove that in one of these finite geometries, there are always going to be the same number of points per line. The other thing is that there are lines, which is to say that for every 2 points, there's exactly 1 line, as we said before. And if you now go through and just pick any 2 arbitrary points whatsoever from among these 25 points, you will find that there's exactly 1 line that passes through those 2 points. And you can kind of already see that this is true, right? If you pick 2 points whatsoever, if you happen to pick 2 points that are horizontally aligned, well, obviously there's just 1 line. If you pick 2 points that are vertically aligned, there's obviously just 1 line. If you pick 2 points that are kind of pass through each other with slope -1, then there's going to be a line from this equivalence class of parallel lines that passes through them. If you happen to pick 2 different points, then you're going to get kind of like a different answer. And if you pick, okay, you can just confirm that that's true. Okay, and what we can extract from these 6 equivalence classes of parallel lines are these 6 squares. 4 of them are Latin squares. 2 of them are not Latin squares, but in fact, to kind of complete the understanding of what's happening here, the very definition of what it means to be a Latin square is that every number appears exactly once in each row and once in each column. But to say that each number, say the 5s, appears exactly once in each row is equivalent to saying that that one of these lines, for example, like this purple line of 5s, never bumps into the same row twice. But the rows are themselves lines. And so you can think of the requirement that each number appears exactly once in each row as saying that any one of these lines, for example, from this equivalence class, can never intersect one of these rows twice. In other words, these 2 squares are orthogonal. So if you expand your definition of orthogonality to refer not just to a pair of Latin squares, but to a set of squares whatsoever, then these 2 squares are orthogonal because 2 ordered pairs never repeat. Because what it would mean for an ordered pair to repeat between these 2 squares is that one of these lines bumped into a horizontal line twice. But if you bumped into a horizontal line twice, then you would have a row of this Latin square with 2 numbers in it, with a number appearing twice in it, which cannot happen. In other words, you can define what it means for a square to be a Latin square by simply saying a square is a Latin square if and only if it is mutually orthogonal to these two squares, the square of rows and the square of columns. The requirement that there be exactly one number in each column can be rephrased as the requirement that these lines be not intersect any one of the column lines twice. And because of some pigeonhole thing, if they don't intersect twice, then in fact they have to intersect exactly once. Okay, so orthogonality with these two squares is what it means to be a Latin square. And so what you end up with when you have a model of order 5, you end up with 6 equivalence classes which give rise to 6 squares. And from these 6 squares, and these 6 squares are all mutually orthogonal. This is kind of proving, the larger point that I'm proving here is that orthogonality is really fundamentally a geometric concept. It's a way of saying that these lines obey basic geometric properties such that they don't intersect each other twice. And so we extract from this a set of 4 mutually orthogonal Latin squares. 4 mutually orthogonal Latin squares. And this shows, I think, that whenever there exists one of these finite fields of a certain order, we can construct a finite geometry of that order, which will consist of lines with n squared, models in which there are n squared points, n points per line, n plus 1 equivalence classes of parallel lines, n times n plus 1 total lines, and from these 6, or from these n plus 1 equivalence classes of parallel lines, we will end up with n minus 1 mutually orthogonal Latin squares. Okay, this is somehow like easy to do. Anyone can do it when the order is prime. If the order is not prime, it's really hard. Tempted to just stop the video here because I'm not sure how many people really want any more knowledge on this topic. But for my many fans at home, we can now attempt something that is like way, way harder. And this thing that is way, way harder is to deal with finite fields in which the order is not prime. Okay, and I'm not really going to explain this, frankly. So this, you might find this, slightly unsatisfying. But off script somehow, we have constructed a finite field of order 4. And a finite field of order 4 exists, but it cannot be quite so easily and simply produced by simply doing arithmetic on the numbers 0, 1, 2, and 3 mod 4. And there are interesting reasons why that doesn't work. Okay, so how do you do it instead? Well, it's some complicated thing, and I don't want to talk about that right now. Instead, I'm just going to give it to you, and I'm going to kind of explain how it works. So here's how it works. I posit that there's this set. I'm calling it Z4. Here is what this set is. It consists of 4 elements. And those elements are 0, 1, A, and A plus 1. Okay, this is a little bit of an unfortunate name, perhaps, for an element, calling it A plus 1, because there's also some addition that we're about to do here. So just really force your brain to see this symbol, A plus 1, as being like a single, indivisible symbol. It's just happens to be a name for this number that happens to have 3 characters to it. Just like the number 75 is a number, but it takes 2 characters, 7 and 5, to talk about that number. Here is just a number, but it's the number A plus 1. Okay, and you'll see in a minute why that's like a really good name, or why that's a convenient name for this number. Okay, so let's go. How does addition and multiplication work in this finite field of order 4? Well, it works like this. First of all, these names 0 and 1 and stuff are not a coincidence. It kind of goes like a little bit like the way Z2 works. In other words, when you add 0 to anything, you get that thing. So that's good to know. And 0 plus 1 is 1. 1 plus 1 is 0. So, okay, 1 and 0 have that kind of same relationship as if we were doing arithmetic mod 2. Hey, also, when you add 0 to a, you just get a. When you add 0 to a plus 1, you just get a plus 1. And so 0 is going to be the additive identity element here. All right, so what happens when you add 1 to a? Well, you get a plus 1. Okay, so it's nice to call it a plus 1 actually, because it kind of reminds us how to add these two elements. All right, and what about 1 and a plus 1? Well, 1 plus 1 is 0, so a plus 1 plus 1 is kind of like a plus 1 plus 1, so that's a plus 0, so that just goes back to a again. Okay, and all right, what else? Similar thing going on over here. A plus 1 is a plus 1, and a plus 1 plus a plus 1 is a. Okay, what happens when you add a and a? Well, this one's maybe a little bit surprising, so I'll just tell you, a and a are 0. So a and a plus 1 kind of cancels out a. Whoa. And a plus 1, well, that's just like 0 plus 1, so that's just 1. Yeah. And over here, a plus 1 is again, a plus a is 0, if you kind of remember that somehow mnemonic. And then here you get a plus 1 plus a plus 1, so that's like 0 plus 0, so that's also 0. Okay, so if you kind of play around with this a little bit, it can start to kind of feel right to you and sort of make sense. That's where I'm at right now. There is also a way, there's a sort of mathematically sound algorithm that can kind of extract this rule, but I'm not going to go into that right now. And okay, what about multiplication? How does multiplication work? Well, 0, the additive identity element, is like a multiplication killer. That is just one of the things that you can prove straight from the field axioms. So that part's not surprising. 1 is, again, the multiplicative identity element. And so that part's not surprising. Okay, what happens when I multiply a and a? What is the understanding behind this? I'm not going to give you one. A times a is a plus 1. And a times a plus 1, this one is 1. Sure. Yeah. That's because it's kind of like a squared plus a. So it's like a plus 1 plus a. So it's like a plus 1. So that one also makes sense to me, but I won't explain. This one is going to then also be 1. And here, if you multiply a plus 1 by a plus 1, that's just like a squared, which is a plus 1, plus 2a, but 2 is just 0. So that's 0. So that's a plus 1 plus 0. So I messed that up. This is just a. Why is that again? A squared is a plus 1. I don't know. Plus a plus 1. I thought I understood it, but maybe I don't. Oh no, yeah, that's right. Yeah, okay. I kind of basically 80% get it, but anyway, no time to talk about that right now. All right, finishing off this worksheet, what can we do with this? Well, I claim, without too much proof or even any understanding, that this set, together with this binary addition-like operation and this binary multiplication-like operation, is a finite field. It's a finite field of order 4. And, okay, can we convert this finite field of order 4 into a finite geometry of order 4? We can. And we do it the same old way as before, with linear equations. But now the linear equations have coefficients in this set. Okay, so the very first thing I asked you to do in this worksheet is to find the line ax plus y equals a plus 1. Okay, how should we do this? I guess we're going to do it, we're just going to do it. So, okay, let's go. I'm going to do it like I did in the other video. I'll just go through the 4 possible x values and figure out what the corresponding y value is. Okay, so being kind of careful now or something, what should we do? We should plug in 0 for x. If we plug in 0 for x, a times 0 is 0, and so you just get y equals a plus 1. So that one was pretty easy. We just get a plus 1. Okay, next, what if x is 1? Well, a times 1 is just a. So this is a plus y equals a plus 1. And now you have to say a plus what is a plus 1? And the answer is 1. So this is true when y is 1. Yeah, not so hard. Okay, now let's plug in a for x. Well, if you plug in a for x, you get a times a. And a times a is a plus 1. So you get a plus 1 plus y is a plus 1. Well, that's true only if y is 0. And finally, if you plug in a plus 1 for x, then you get a times a plus 1 plus y equals a plus 1. But what is a times a plus 1? It's 1. Okay, so this final line is saying 1 plus y is a plus 1. But what do you have to add to 1 to get a plus 1? Answer a. So here we get a. All right, how can we make sense of this? We can now graph, we can just all the points which satisfy this model. So you get 0, a plus 1, so I'll put that there. And 1, 1, you put that here. A 0, you put that here. And a plus 1, a, you put that there. Okay, so it's hard to understand this line geometrically, but that is one of my lines. Okay, and was there a cooler way to do this? Maybe you could have, what can you do? You can maybe move this ax over to the other side. So you can write this as y equals negative ax plus a plus 1. But then negative a is kind of weird potentially. So what's the additive inverse of a? What do you have to add to a to get 0? Answer a. So negative a is really just kind of like a. So these are all three different ways of saying the same thing. Y equals ax plus a plus 1. And so if you want to, you can think of this as the line with slope is a and the y-intercept is a plus 1, which is kind of a little bit making sense over there, except I don't really know what the slope of a is. All right, well we then have, in addition to this line, y equals a, I'll put it over here. In addition to this line, oh yeah, that was what I meant to say. Y equals ax plus a plus 1. We're going to have 3 more lines. We're going to have the line y equals ax plus a, which I'll represent with a green triangle. Then you have, no, I don't want to do a green triangle. I'm trying to match it to my key. So okay, let me just write them all out. I'll just write them all out in the same color. So you have y equals ax plus a, y equals ax plus 1, and y equals ax. What is this? It's a set of lines that are all parallel to each other. And let's draw them right now or something like that. So first we'll do the triangle one. So what is the triangle one? The triangle one, or if you prefer, I can write this as ax plus 0. That's kind of like better, I guess. Okay, what is this triangle one? Well, it's all the points that satisfy this equation. So it's all the points where y is just ax. Okay, well, a times 0 is 0. So if you plug in 0 for x, y has to also be 0. So I think it's pretty clear that the triangle goes through here. And then am I going to do all this live? I guess so. I'm just going to do this kind of in my head in a way that's barely comprehensible. If you plug in 1 for x, you get y is a. So 1 comma a. Yeah, this is not so hard. Yep. What about if you plug in a for x, you get a squared, but a squared is a plus 1. So you get a comma a plus 1. And finally, if you plug in a plus 1 for x, you get a times a plus 1. But a times a plus 1 is 1. So that's how you end up here. Okay, so that green line is another line which is parallel to that purple one. Okay, 2 more to go. I'll make a orange star now. What is the orange star? It's all the lines that satisfy y equals ax plus 1. So now, let's see, if I plug in 0 for x, I get y equals 1, so 0 comma 1. And then if I plug in 1 for x, I get y equals a plus 1. So 1 comma a plus 1. Looking great. Then if I plug in a for x, I get y equals a squared plus 1. But a squared is just a plus 1, and a plus 1 is just a. So I get a comma a. Yep. And if I plug in a plus 1 for a, I get a times a plus 1, which is 1, plus 1, which is 0. So I get a plus 1 comma 0. And finally, I will use a pink heart to refer to the line y equals ax plus a. Again, talking this out, if I plug in 0 for x, I get y equals a, so I'll have a point 0 comma a. If I plug in 1 for x, I get y equals a plus a, which is 0, so I get 1, 0. If I plug in a for x, I get a squared, which is a plus 1, plus a is 1, so I get a comma 1. And if you plug in a plus 1 for x, you get a times a plus 1 is 1, plus a is a plus 1, so you get a plus 1 plus 1. Okay, what have we just done? I have created one of the 5 equivalence classes of parallel lines in this 16-point model. As this is a finite field of order 4, there will be 4 squared equals 16 points in the model. And every line in this model will pass through exactly 4 points or have 4 points on it. You're going to have one set of parallel lines that are all the horizontal lines. You'll have another set of parallel lines which are all the vertical lines. And in addition to that, you're going to have 3 more equivalence classes of parallel lines. And one of these equivalence classes of parallel lines I have just constructed right here. This is basically all the lines of the form y equals ax plus k. In other words, it's all the lines with slope a, whatever that means. From this, of course, there is a Latin square that we can extract, and this Latin square is, hold on, is the one dictated by this geometry. So what do you have? You have, I'll just do it like this. 1, the purples are 1s, let's say. So 1, so now for a second, made my square too big. There we go. 1, 1, 1, 1. Then you'll have the line of 2s. So that's 2. I'll make my heart 2. 2. You'll have the line of 3s. I'll use orange. So 3, 3. I'm just looking at that picture over there. 3 and 3. And you'll have the line of 4s. So 4, 4, 4, 4. Okay, what is this? It's a line square. That alone is not so impressive. But what is impressive is something that I'm not going to do right now, but which you could totally do if you put 10 to 15 more minutes into this activity, which is consider the other. So you have now, like I said, you have the x equals k equivalence class of vertical lines. You have the y equals k equivalence class of horizontal lines. You have the y equals ax plus k lines that we just did. I'll put those here. Y equals ax plus k. This is the equivalence class that we just made a picture of. But then there's also, of course, the y equals like 1 times x, let's say, equivalence class. And there's also the y equals a plus 1 x plus k equivalence class. That is the equivalence class of lines with slope a plus 1. And if you did everything we did here all over again, it would really maybe only take you like 5 minutes. from this equivalence class of parallel lines, you would get another Latin square. And from this equivalence class of parallel lines, you would get another Latin square. And those 3 Latin squares would be mutually orthogonal. Or if you prefer, you would end up with 5 squares, 2 of which are not Latin squares, but mutual orthogonality with those squares would make all of these squares Latin squares. And so what you end up with when you're all done is 3 mutually orthogonal Latin squares. And this is the way to sort of construct these sets of mutually orthogonal Latin squares that Gossett, our textbook author, just gives them to you. And I will also be doing that on the test tomorrow. Okay, I hope you have learned something about Latin squares, about finite geometries. What properties do these finite geometries have? I think I forgot to say one thing about them. They have these, the sort of boring axioms are the ones that say there are at least 2 points per line, and that there must be at least 2 lines in the plane. But the 2 really contentful axioms are the one that says through every 2 points there's exactly 1 line. And then the third one, which is what makes it an affine geometry specifically, is the parallel postulate. Through any line and any point not on that line, there is exactly 1 line parallel to it. And so, for example, if you take this line of stars, and you give me the point A, comma 1, there's exactly 1 line, namely the line of pink hearts, which is parallel to the line of orange stars and passes through the desired point. So that's certainly something that's true in normal Euclidean geometry. Through a line and a point not on that line, there's exactly 1 a line parallel to it. But that also works in these finite geometries. And if you happen to pick the point, a line and a point that's on that line, then the parallel line is that line itself. Throughout this entire video series, I have been insisting that every line is parallel to itself. That is what went into declaring that these are in fact equivalence classes. Parallelism is equivalence in this system because every line is parallel to itself. Parallelism is symmetric. If line A is parallel to line B, then line B is parallel to line A, and also parallelism is transitive, which is a feature of affine geometries with the parallel postulate. And so since parallelism is transitive, then parallelism is an equivalence relation. So we have these equivalence classes, and hopefully you have a deeper understanding of finite fields, of these finite discrete geometries, the relation to Latin squares, and the relation to orthogonality. Okay, sorry I didn't make this video 2 weeks ago. Goodbye, everyone.